And welcome back, or welcome to those of you joining me for the first time. But to my Regents Physics class, welcome back. Uh, this is the lesson for Unit 10, Lesson 4, and we're going to be talking about the characteristics of sound waves today. I had thought, planned, thinking, how could I creatively do this lesson? And one of the things that occurred to me was I could do it silently. I'd have to do it through writing. I'd have to do it through gestures, but I don't know American Sign Language. Um, I'd have to do it through non-vocal method of communication, uh, just to emphasize the point that a lot of the way that we pass information back and forth to us is through the medium of sound, through the medium of air, all right? Sound waves coming from me, moving through the air to the microphone on the laptop, and then out through the speakers to your ears are conveying more information than just you sitting there and seeing my lips move back and forth. Okay? Sound. How is sound made? Well, there's lots of ways. There. I just created a sound. I didn't use my vocal cords to do it. Sound is created, or sound is a change, a violent change in the pressure around a substance. Okay. You can cause sound to move through a solid substance, and it isn't until it encounters air that we perceive it or not. For instance, earthquake waves. All right. Earthquake waves happen deep under the ground, and they are a sonic uh, movement, pressure wave through the earth, through the solid matter of the earth. And then once it encounters the air, then we'll hear, that pressure wave created by the displacement, the movement, the shift of the rock deep in the earth's crust. Okay? Sound waves cannot pass through a vacuum. And that is where an awful lot of science fiction films, the people that write them make a decision. Oh, we're going to have more dramatic moments here, and we're going to have sound in space. Some of the best science fiction, though, is ones that keep that science real. Okay? So, what are the qualities of sound waves? Okay. First off, definition for sound, all right? Sound. A pressure wave that passes through a particular medium that we perceive with our ears. Okay? Now remember that sound requires a physical medium because it is quite literally the the scrunching together of the molecules and then the separation. But this scrunching together pulls these molecules over toward it. Well, that pulls these molecules and then it pushes out from there. That pressure wave then propagates through whatever the substance is, and eventually that pressure wave reaches our ear, vibrating our eardrum and doing interesting things inside the ear that then create nerve pulses that our brain perceives, and we call it sound. Okay? Now, speed of sound. Since sound is a wave and it's traveling from place to place, we can measure its speed. All right? The speed of sound depends on three qualities of the medium. First off, its physical density. All right? Second off, the elasticity of the medium. And thirdly, the temperature of the medium. Okay? Now, how each of these affect the speed of sound, I'll get into momentarily. And with the magic of the pause button, I can get that out of the way and appear before you video magically. Okay? Um, okay, so how does physical density affect the speed that the sound wave will move through something? Okay, well, let's think about it. Physical density represents the amount of matter in a given space. So, if there were more matter and sound is the pressure wave of these particles scrunching together and pressing apart, if there was more matter in a given space, would sound move more easily or would it be harder for sound to move through that? Well, think about it. It represents the number of collisions that can take place. That pressure wave is the collisions going through. So if there's more chance of a collision happening, it's more likely that the energy of that collision gets passed on. So the denser a material, the faster sound will move through it. Interestingly enough, sound moves through air at a particular speed. We'll get to that speed momentarily. Sound moves through water at 5 times that speed. 5 times. Sound moves through steel 5 times faster than it moves through water, meaning sound moves through steel 25 times faster than it moves through air. All right. Sound moving through steel, that's one of the fastest ways to get sound from one place to another. All right. It's very interesting how quickly sound will move through solid matter compared to liquids, compared to what we're speaking in. The reason that we speak this way is because we breathe and we've evolved to make noises in this kind of matter, gaseous matter. All right. Do we know creatures whose form of sonic communication does not use air? And if anybody said, hey, what about whales and dolphins? There you go. Okay. Lots of aquatic creatures produce sounds, but they produce sounds that are particularly good at communication through water, but not through air. All right. Okay. Second quality, elasticity of medium. Remember that elasticity from earlier in the year, we talked about the elasticity of a medium as how strongly the internal forces that hold the matter together, how strongly they want to return something to their original positions after they are disturbed from that. Okay? And so the more elastic a material is, the more strongly it wants to hold its shape, the more strongly it's going to transmit energy by those same elastic forces. Therefore, the more elastic something is, the faster the sound will move through it. Interestingly enough, while lead is denser than steel, sound moves slower through lead than it does through steel because lead is a much less elastic material than steel is. If you pound lead, it stays pounded. If you pound steel, it returns. It doesn't dent as easily. It doesn't dent as quickly. Yes, you can, but it doesn't do it as easily as lead would. Okay? Final thing, temperature. Now let's remember our sciencey definition of temperature. Temperature represents the average kinetic energy of the molecules of substance. Kinetic energy, the energy of motion. So, if I have something with a high temperature, those molecules are going to be bouncing and bashing around very quickly between each other. If it's a solid matter, they're really sitting here and smashing away really quickly. If it's a low temperature, they might be doing this. So, in which of those instances is it more likely for additional energy to get transferred between the molecules? Well, if they're already smashing around really quick, it's more likely that that added energy gets transferred as part of those collisions. So the higher the temperature of a substance, the higher the speed of sound in that substance. Okay? So those are the three determining factors that determine the speed of sound in a given medium. So, since we, the human species, are concerned with what things affect us in science, all right, and speed of sound is one of those things in science that affects us. And because we exist out here in the air, we're worried about what's the speed of sound in air. All right, that's what we base everything on. Okay, so speed of sound at standard temperature and pressure, which is 0 degrees Celsius. The speed of sound at that temperature is 331 meters per second in air. All right. Now, when was the last time you ever had a class in a room that was at standard temperature and pressure? I don't think you've ever had a class. It may have felt like it was freezing, but I'll tell you, the coldest temperature in my room was 10 Celsius, okay, which is equivalent to about 52 degrees Fahrenheit, all right? So it wasn't ever freezing, but yeah, sometimes my room was pretty darn cold, all right? So the speed of sound, because sound is temperature dependent, the speed of sound at another temperature, well, we use this formula, 331 meters per second plus 0.6 times the temperature in Celsius. So that means that if it's a below zero temperature, you're going to get a minus over there. If it's above zero, meaning room temperature, all right, or any other temperature for that matter, the speed of sound is going to be above 331 meters per second. At normal room temperature, which is usually 20 degrees C, if we multiply that over there, we get 346. I think I did my math right. I may have gotten that 343.6. Maybe I got it wrong. I might be 343.2. I did my math wrong. Sorry, it was mental arithmetic. My bad. Sorry to the world out there. Oh, I will make amends for that in the future. Okay, sound as a wave. So we have the wave characteristics of wavelength, speed, frequency, amplitude. Okay, those are the characteristics that we've talked about for all waves. So for sound, we have particular names for those particular characteristics. For a sound wave, pitch is the name we give to frequency. All right. So if I were talking like this, it's a high pitch. If I'm talking like this, it's a low pitch. All right. The speed of the sound is not pitch. The frequency of the sound is pitch. Sopranos are considered to be high pitch singers. Basses are considered to be very low pitch singers. Baritones, tenors in the middle. A tenor is a higher pitch singer than a bass, but a lower pitch singer than a soprano. Some tenors would argue with me about that, but I have a wife who is a soprano, a coloratura soprano, and she prides herself in that she doesn't know of any tenors that can match her high notes. Alrighty. Human hearing. Okay, so what pitches do humans hear? All right, humans hear from wavelength or frequencies as low as 20 hertz to infants and small children can hear 20,000 hertz or 20 kilohertz. Okay, I can no longer hear those frequencies. There's an app that you can get on the iPhone or the Android that actually tests for the pitch that you can hear. Okay, and you can set the frequency and start it at 20,000. And if you hit it and you don't hear it, you know that you are not at the top range, the possible range of hearing. Now, this created an interesting situation for me. A while ago, shortly after I taught this particular lesson, I hadn't known that this was out there. This is probably 10 years ago now. Somebody had on their iPod, and this was before all of that was around. The iPhone apps. The iPod had this app on it, and you could use it to, I don't know, pass information from one individual to another through a form of Morse code or whatnot. I don't know. It was being used for nefarious purposes in classrooms. Okay. Um, and it was because teachers generally couldn't hear the frequency that was being tapped out using this. And it happened to have been done to me, and but it wasn't done quite nefariously. It was done annoyingly. All right. One of my students decided he wanted to annoy his classmates, and so he brought his iPod in. He had a little kind of external speaker thing going on, and he would hit the button, and it would make the clicking noise that you would hear. I didn't react to it. I didn't hear a thing. Okay, because my top range of hearing right now is about 15,000, 15,000. And so he must have had it set at like 17 or something like that. And finally, one of my members of my class said, "Whoever's doing that, stop it." I went, "What's going on?" And she proceeded to tell me that she said there was somebody that was making a beeping noise in the class. And I said, "I don't hear anything." And a couple other kids in the class said, "Oh, I don't hear anything." But then half the class said, "Oh, yeah, there's been this annoying beeping, and it's intermittent. It's going on." And I saw the kid putting his stuff away. And I went, "Get it out. Let me see what's going on." Sure enough, he had his, I saw the speaker, and that's the thing that clued me in. The speaker was about this. It was one of these tiny little personal, early on, interesting uh, device. And so I said, "Well, let's do a test here. You know, tomorrow we're going to be taking a quiz on this, and during the quiz, I'm going to uh, do this. And every time that I turn it on, I want you to put a check mark. Make a box at the top of the quiz and put a check mark in the box, and You'll count how many times that you heard me turn it on." And so they let me do it. And so during the quiz I set as 10 minutes. And so I would reach over and I would touch. And sometimes I would turn it on and sometimes I wouldn't. So I knew that I was only going to do it a certain number of times. And so I remember one kid turned it in, and I remember reaching over, and I believe I did it 8 times, but I only turned it on 5. He had 8 check marks. I had another kid who had 8 check marks. I had 2 other people that had the 5, and then I had a bunch of them had nothing. Interestingly enough, they were also the same kids that had the early earbuds and headphones, and they listened to their music too darn loud. Their hearing was as bad as mine. Okay? Hearing naturally decreases with age. All right? It's a natural consequence. The more times you listen to loud, sustained sound, for instance, construction workers that don't wear ear protection, their hearing decreases dramatically over time, and it can create permanent hearing loss. For more about the physiology on that, you can talk to me at a different time. Okay, so hearing, human hearing range 20 to 20,000, but that decreases with age. My current upper range is between 14 and 15,000 kilohertz. Okay, All right. Now we have two other terms for frequencies that are above 20,000 and frequencies that are below 20. Okay. Ultrasonic frequencies are those sounds that have frequencies over 20,000 hertz. Okay. Lots of animals hear in the ultrasonic. Most birds do, bats do, dogs can hear in the ultrasonic ranges. Okay. Dog whistles, we don't hear the dog whistle, but you can blow it and it gets the attention of a dog. You can train it by blowing certain signals. Two longs and a short represent come to me. Two shorts and a long represent go fetch. Three longs, sleep, play dead or something like that. All right. And that's how you can use the dog whistle silently to command a dog to do things around you. And you wouldn't have to say, come, sit, roll over, play dead, fetch, what have you. Now, infrasonic. This is a relatively recent discovery. I mean, yes, we know that waves can be made with frequencies lower than 20 hertz, but we've only found within the last 2 decades that there are two species of animals that communicate infrasonically in air: elephants and giraffes. The giraffes were the most recent discovery. They were within the last decade that we realized that giraffes are not mute. They actually do communicate, but they communicate in very long wavelength, very low frequency sounds. Okay. And it has something to do with, obviously their long necks and the length of their vocal cords and the shape that they make the sounds. Okay. But it's very interesting. Giraffes are no longer considered mute. All right. Because we started thinking about, okay, if sounds can be made above what we normally hear, are there creatures that communicate with sounds below what we normally hear? We discovered that elephants, infrasonic sound travels much longer distances because of the long wavelength that it is, travels much longer distances through the air than regular normal sound waves. Okay? The amplitude of a sound wave is volume or loudness. Okay, the sound intensity, how strong the sound is, how loud the sound is an indication of its amplitude. Okay, we measure it with a unit called a decibel, and a decibel represents a ratio of pressure. All right, it's a ratio of the overpressure that the sound wave is making compared to normal atmospheric pressure. All right. This is actually a logarithmic scale. And so what that means is every multiple of 10 increase in the volume represents a doubling of the loudness of the sound. The logarithm is on, it's an exponent of the power of 2. So the threshold of hearing is 0 dB. All right. I hope you heard that sound. The sound that I'm making right now is between 40 and 60 dB. All right. So a 30 dB lullaby. Mother singing very quietly to her child. Father singing very quietly to his child. 30 dB. Barely enough to be heard. That is twice as loud. So is twice as loud. Okay? Now, let's go to the other extreme. Most rock bands try to be as loud as possible. Okay? 100 dB is a very, 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 very loud sound. Okay? And so a 100 dB rock song is 32 times louder than a 40 dB conversation. 40 dB is about this level of sound right here. Okay, so this represents normal conversation. You know, somebody sitting across the table from me, da 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 da, we're having a conversation. If we were to measure the pressure waves, the volume of this, it'd be about 40 dB. All right, I can't quite yell to 100 dB. I think I can get to 80 or 90, but not 100. All right, so this is 6 multiples of 10, right? 40, 50, 60, 70, 80, 90, 100. 6 multiples of 10. So, double, quadruple, octuple 8 times, 16 times, I don't know what that is, 32 times, oh, this is actually 64 times louder. Yeah, that should be 64 there. Okay, so 64. 2, doubling, quadrupling, 8 times, 16 times, 32 times, 64 times. Okay, so it's a power of 2. Every multiple of 10 increase in the dB is a power of 2. It's the exponent on the power of 2 for the doubling of the loudness. And finally, we have the quality of a sound. All right, quality of a sound. All right, let's say a violin is tuning at an orchestra and an oboe are tuning at an orchestra. Both of them would be playing the same note, but you can easily tell the difference between the oboe making tuning A and the violin making tuning A. All right, and we call that ability to distinguish between two sounds that are essentially the same sound. They have the same basic frequency. We call that quality timbre. This is pronounced timbre, not timbre, timbre. Think of it as T-E-M-B-E-R. And no, you don't say it as in timber. We're not a lumberjack. All right? Timbre. Timbre is the quality of sound that allows us to distinguish between two sources making the same sound. Interestingly enough, if you call my house here and my son answers the phone, the timbre of his voice is so darn close to mine that you can't tell us apart. It's very difficult over the phone. Okay? So timbre is something that is based upon how the sound is being made and the overtones and harmonics that happen to be made with it. So there you have it, sound. All right, sound in all its forms is an amazing thing. We use it for art, we use it for music, we use it for communication. All right, sound is a wave. Sound is a pressure wave. It's the displacement of molecules in a substance and that vibration passing down through the substance. We happen to be able to hear it because of how we use air, but sound can also be made in water. Sound can be made in solid matter. All right. And all of the properties of waves that govern how waves move from one place to another in a material, how they change as they cross a boundary from one material to another, that is all useful for describing how sound works. Once again, it's your friendly heaven physics teacher signing off and hoping that you have a wonderful day. All right. Hope to see you soon.